Okay, welcome to the final event of the hottest summer school. Today, we will have Chaitanya, Leena, Subramaniam, who will be talking about the semantics of HoTT. Please go ahead.
Thanks, Dan. And as I was mentioning to Dan before the talk, I must apologize for my slides today. They were made in a rush because I found out to my unpleasant surprise last night that my graphic tablet isn't working. So I don't even have a Blackboard to answer your questions, but I'll try to answer them as best I can nevertheless. And so please, if you have any questions about the slides, or if you notice any errors on the slides, I'm sure there are lots of errors on the slides, feel free to, or please, interrupt me and point out anything that doesn't make sense, or everything that doesn't make sense. Okay, so the semantics of HoTT. Before I begin, I'd also like to say that I really found this summer school quite exciting. I kind of stopped following it after a bit after say the first few weeks, but I did try to catch up before this talk from the YouTube channel, and I found the talks were on the whole really accessible, and that the audience was clearly very interested and spread out over the globe with lots of different people, and that's really a great thing. So thanks to the organizers. Maybe as the last speaker, I'd like to thank the organizers before I begin. All right, so semantics of HoTT. The first question you might ask is, why semantics? Even before what is semantics, but why does one care about something outside of HoTT? Well, semantics is a way to understand what we're saying using our syntax, but it also allows us to describe and discover properties about the syntax. So semantics allows us to prove things like soundness and completeness, and avoid obvious inconsistencies in our syntax. But it also allows us to understand better certain constructions that we might know only syntactically by abstracting them into more recognizable algebraic form, as we'll see. And it also allows us to discover, let's say, mathematical facts by proving that a certain object is a model of our syntax, and therefore anything that we can say in our syntax has meaning with respect to that object. And that allows us to give some kinds of, allows us to discover certain, let's say, synthetic truths that when applied to a given model turn out to be actual meaningful statements. And finally, I feel like this is a sticking point for a lot of more traditional mathematicians, which is that HoTT resembles homotopy theory or abstract homotopy theory a lot, but how does one really know that what you're doing in HoTT is homotopy theory? And as we'll see, that's probably what this talk is going to focus on. Okay, so the kind of semantics I'm going to talk about is describing models of type theory and of HoTT as functors. So it's called functorial semantics, and this is something that was introduced in, I guess, the just about the midpoint of the 20th century by Lovere and other people, Benabou, which essentially follows the same procedure irrespective of the kind of theory that we're talking about. So let's say we're talking about a type theory, some kind of type theory. The way functorial semantics works is that the first observation to make is that the syntax of our theory forms a category. So there is some category that we can associate to the syntax, called, not surprisingly, the syntactic category. And once this category has been constructed, then a model of our theory can be seen as simply a structure-preserving functor from this category. Now, what the structure is depends on the theory itself, but a model is always some functor, some pre-sheaf, if you like, valued in an arbitrary category. Moreover, it so happens that the syntactic category that we construct is initial among all categories with the right notion of structure and morphisms of that structure. And therefore, finding a model in some arbitrary category is exactly the same thing as describing a given structure of that kind in that category. So, for example, a model of the theory of groups in a category would be a group in object in that category. That's one example, one say, traditional example of functorial semantics. Right. So how do we apply that to HoTT? The first construction is that of the syntactic category. Now, the syntactic category of any type theory only requires there to be certain rules that are the structural rules of Martin-Löf type theory. And if you followed the summer school, you recognize these rules. So they're the rules for contexts and variables, weakening, and substitution. And when I write an arbitrary judgment here, I mean a judgment of something being a type or something being a term of a given type. And substitution here is substituting out the variable x for the term a. So I think this notation is familiar to you. All right, so given these rules, how does one describe a category associated to any type theory that has these rules? In particular, let's say HoTT. Well, the objects of this syntactic category are contexts. So they're lists of variables which are typed and such that each xi is a variable of type ai in the preceding context of variables. So every type can depend on all the types that precede it. Morphisms are what are called context morphisms. So a morphism from a context delta to a context with k variables is a list of terms of length k, such that each term is typed in the following manner. So T1 is of type A1, A1 being a type in the empty context, and finally Tk is of type Ak, where all the preceding variables of the context that's the target of this morphism have been substituted out for the preceding terms, T1 to Tk minus 1. Then the identity morphism is just the list of variables x1 to xk. So that's the identity morphism on the context x1 of type A1 to xk of type Ak. And composition is defined by substitution. So maybe I'll ask a question. Is this clear at this point what this means? So if I substitute x1 to xk in any list of terms that use the variables x1 to xk, I get back that same list of terms, and that's why it's the identity morphism. Right? And composition of substitutions is simply, and this is where I would love to have had a blackboard, is simply substituting a list of terms for the variables that another list of terms uses. Given that in the definition of a context morphism, every term in this list uses exactly the same variables. You see that the context delta doesn't change. And so if we plug another list into delta, then we can substitute all of the variables in delta that each of these terms can use with all the terms in that list that we've plugged into delta. And that's what composition of substitutions is. And syntactically, composition of substitutions is strictly associative. And so this defines a category. And that's it. I mean, we've defined a category. Oh, I think there's a question. So yes, so variables are particular kinds of terms, which is why the identity morphism is a list of variables, but morphisms can use terms in general, yeah. So the target of a given morphism is a context, namely a list of typed variables. And a context is once again given by this list of rules. That is, a context, a judgment that something is a context is a tree that ends in a conclusion of this form. Okay. Right. So this thing is a category, but we still have to describe what kind of structure it has, because we're not out of the woods yet. In order to define what a model of this such a type theory is, we need to say that it's a functor on this category, but a functor from this category, but that preserves certain structure. Okay, so let's see what structure we get immediately from the syntax. The empty context, well, it's a context. It is also a terminal object. Why so? Because the empty substitution is the only map that exists from any context to the empty context. The empty substitution, the empty list, is a list of terms, etc., that satisfies the data for the requirements of a context morphism. And so the empty context is a terminal object. Moreover, given any type A in a context gamma, we have a dependent projection, a morphism that's called a dependent projection. That's just the list of variables that leaves out the variable x, that forgets the variable x. Right? Does that make sense? This is the context morphism that just drops the variable x. And that's given by the weakening rule. If you look over here, right? So, right. So, and if we have a list of terms from delta to gamma, then, well, we can substitute the judgment using the substitution rule. We can substitute the judgment of A being a type in the context gamma into a judgment of A in which all the variables that A might eventually use have been substituted by the terms in the context morphism tau is a type in delta, and therefore we can construct the context delta extended by this new type, a variable of this new type, of this substituted type. Then it so happens that in the contextual category, this square, well, this square obviously commutes because the morphism upstairs is just tau with the variable added, and then both these things just drop the variables at the end. And so the square obviously commutes, but it's moreover a pullback square. So a little bit of category theory. Hopefully people know what a pullback square is. All right. So that's something that's a nice exercise to go home and prove. I won't do it over here, mainly because I don't have a blackboard, but it's not too difficult. Next, for any context, we can consider the category of extensions of that context with a variable of a given type. So that's exactly what this definition says. So it's a full subcategory of the slice category over that context, whose objects are the projections that drop the last variable. And substitution, the previous thing that we've defined over here, then defines a pullback functor. So what I mean here is that if we apply substitution to the map tau being this projection, then we get pullback functors between these categories of types. So categories of types over gamma, categories of types over the category of types over gamma extended with x of type A. Does that make sense? Right. And so then it turns out that the rules for sigma types and the rules for pi types provide left and right adjoints to these pullback functors. So to pull back along one of these dependent projections, not along an arbitrary morphism, but just along one of these dependent projections between these categories of types has a left adjoint and a right adjoint. And the left adjoint is the construction of sigma types, and the right adjoint is the construction of pi types. In the introduction elimination rules provide the data of the two adjunctions. All right. So here are the rules for identity types. So the identity types are defined as follows. I'm not sure if you've seen these diagrams drawn before in the course. I don't really remember them being drawn, but so this is clearly the introduction rule. So by that, I mean the solid part of this diagram are the hypotheses of the introduction rule, and the dashed part of the diagram is the conclusion, right? So given the identity type, there is a reflexivity proof that is essentially just a section over this diagonal morphism, right? The elimination and computation rules are given by this data. So the solid data, again, in this diagram are the hypotheses, and the dashed data is the conclusion. So what that says is that given a type C that depends on the identity type of A in gamma, right? And given an element of C that lives over the reflexivity proof, right? That's this thing up here. And the commuting diagram says exactly that it lives over the reflexivity proof. We can extend it to a section, right? This thing here is a section, namely a term, a global element of the type C over the context of all identity proofs, right? That's the J. And the computation rule then just says that composing J with reflexivity gives you back the original term C. Right? Okay. Does that make sense if I write things out like this? All right. So if people who've done a little bit of homotopy theory are coming to see this, you start seeing something that looks a bit like path objects and something that looks a bit like a lifting condition or some kind of lifting property of a fibration with a trivial cofibration or something like that. Which category does the proof live in? So for now, we're always working in this category, in the category of contexts, the syntactic category. Objects are contexts and morphisms are lists of terms, blah, 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 that are context morphisms. So all of these diagrams are in that category. All right. Okay, so what about a universe? So a universe, well, I won't get into details of what kind of universe and hierarchies of universe, et cetera, et cetera. Essentially, what a universe says is that given a map from a context, that it is a type. There is a type U that doesn't depend on anything. And given a map from a context into U, there is some choice of pullback square of some type that depends on U. So I mean, the way I've written it is X of type U, little x of type X, and the choice of pullback is some dependent projection over gamma. So that's some type that lives over gamma. And why does this suffice? Well, because if you take delta and you take a morphism into gamma, then substituting with this morphism gives you, by pulling back, the composite, a choice of pullback square for that lives over delta. So in a sense, this is all that a universe gives you, an arbitrary universe. And this thing is easy to categorify. So in some category, it's just a map along with, for every morphism into the codomain of the map, the target of the map, a choice of pullback square. That's it. I think this definition is due to Voevodsky. I'm not entirely sure, but it's a very neat and elegant definition of what a universe is in a category. All right, so any questions up to now? All right, script U is an object in that diagram, meaning it's a context, yes, but it's also a type. So it's a context of length 1. There is actually more I can say about lengths of contexts and stuff like that, but that would take me a little far away from but there's more structure than what I've just described in this category of context, the syntactic category. But I don't have time to get into it, and yeah, especially if I want to get to higher toposes, for example. So there are 2 ways to look at it. So this is some kind of type universe. So you could also say that a type universe, that every type lives in the type universe, let's say, or a type universe. So you have to have some kind of hierarchy of type universes. So here I'm just describing a type universe. So this could be in a type theory where you have types that don't necessarily belong to this universe. But yeah, in general, we would like to say that there's one universe and all types belong to that universe. So I think you saw modalities, right? So modalities are an example where you could have something that's called a sub-universe, and you could have things that belong to the sub-universe, and therefore also to the universe, but you could also have things that belong to the universe that are not modal, so they don't belong to the sub-universe. Right, so that's an example. Okay, so just a little bit of category theory so that things don't get too hairy too quick. I'll say that an object of a category is squareable. I don't really like the terminology, but it's not clear for me. If binary products with that object exist in the category. This is the same thing as saying that the obvious functor from the slice category that just forgets the codomain, right? So map from y to x, you just spit out the object y, that has a right adjoint. And we say the squareable object is exponentiable if this right adjoint itself has a right adjoint. So that's called the exponentiation with x, I guess, the power object. I think some people say powerful for exponentiable, but yeah. And a category has finite products if it has a terminal object and if every object is squareable. And it's Cartesian closed if it has a terminal object and if every object is exponentiable, right? So that's what a Cartesian closed category is. If people have seen this, I'm guessing some of you have seen this, if not most of you. And a map in a category, now this might be something that's a little less familiar, is squareable if all pullbacks along this map exist, right? And this is the same thing as saying that the functor of post composition with this map, so that goes from the slice category over the domain to the slice category over the codomain, has a right adjoint. That's the pullback functor. And we say that a squareable map is exponentiable if this right adjoint has a further right adjoint. And a category is locally Cartesian closed if all its maps are exponentiable. This is equivalent to each slice category of the category being Cartesian closed, and it's a standard exercise in category theory to show the equivalence. It's not completely trivial, but it's a nice exercise. Right. So why are we going to locally Cartesian closed categories? Well, there happens to be a very old and traditional way, I would say naive way of modeling dependent type theory in locally Cartesian closed categories, which stems from the model of dependent type theory in sets. So the original model of type theory, of dependent type theory in sets, models contexts as sets and types as indexed sets. So this is the types as sets paradigm. Maybe somebody spoke about this at some point. The idea is that a dependent type is, in a context gamma, is a family of sets indexed by the set that interprets gamma. So here A gamma, A little gamma is a family of sets for each little gamma in gamma. And then given a dependent type in the context gamma, the context that's gamma extended with a variable of this type is simply the disjoint union of the elements of the family. Of course, families of sets indexed by a set are the same thing as functions into the indexing set, right? Each element in gamma, the fiber over that element is just the element of the family that's indexed by little gamma. So this you can also describe this as types as functions model. Terms in this model are sections of this projection. And this makes sense because terms, if you unwind the definition of a context morphism and the syntactic category, you'll find that terms are exactly sections of the syntactic dependent projections. And in this model, terms are also therefore sections of these projections. And then sigma types and pi types have a canonical construction, which is that given a sequence of composable functions, so that's families indexed by another family indexed over gamma, we can define the sigma type by taking the disjoint union of elements in a family, certain elements in the family, the elements that are indexed by people living over an element gamma. And similarly, we can take products, so the product of sets indexed by a gamma to be the pi types. And this gives the right definition in terms of adjoints, which is what we need to interpret the syntax as, since already at the level of syntax, sigma types and pi types are adjoints to some functor. However, we run into something curious with identity types, which is that, well, we need to interpret the identity types like they behave in syntax. And so we have our two triangles here, where at the bottom we have, here we're just taking the identity type of some type A, not in any context gamma. We have a section over the diagonal, and we have the square corresponding to the elimination and the computation rule for any family over the identity type. But however, we've just seen that we can interpret a type in context as any function. And therefore, this function, the function that interprets the reflexivity term, is itself a type in context. And therefore, applying this rule to the type in context C over the identity type being reflexivity just says that reflexivity is an isomorphism, and therefore that the identity type is exactly the diagonal of A. And so it's a monomorphism in sets. What that means is that its diagonal, which is the identity type of identity proofs of A, is an isomorphism. So that means that each of its fibers is contractible. And that is exactly saying that all types in the set model are zero truncated. It's also called the uniqueness of identity proofs. So the set model in particular cannot hope to have something like a univalent universe. And this argument is more generally true in any locally Cartesian closed category, and moreover, a counter model in groupoids was used to prove that UIP is independent of dependent type theory with identity types. But right, so LCCCs are somewhat not quite adequate to model type theory in a homotopy theoretic way. Right. So, however, LCCCs have enough structure and a lot of helpful structure to allow us to model sigma types, pi types. And indeed, we can find LCCCs with universes that that allow us to give a succinct definition of what a model of type theory in such an LCCC is. That definition goes as follows. I'm not going to unwind what I mean by the last 2 points, but this is essentially the same semantically as what you've seen with syntax, where you can define type formers using a universe rather than using inference rules. So you can define identity types using a universe and their introduction rules, and even their elimination rules using a universe. This is basically doing the same thing in the internal language of a locally Cartesian closed category, using a universe in that category, as we have seen the categorification of the notion of universe. So that's what I mean when I say to be in the universe. All right, but it's useful to note that given an LCCC with a chosen terminal object and a universe, it's possible to define a complete model of type theory in that LCCC, as long as this universe is closed under sigma and closed under pi. And when I say type theory here, I mean only sigma pi in the universe. All right, so this is somewhat helpful because among such nice LCCCs are categories that allow us to model identity types in a homotopical way. And this is an idea that I suppose was around at some point and that different people stumble upon independently, but I know only of one reference where it's described in generality, and that's a paper by Awodey and Michael Warren, which is that in such an interpretation, types and contexts are not interpreted as arbitrary maps of a category, as they would be in, say, just a bare locally Cartesian closed category, but as fibrations of something that's called a model category. Now, unfortunately, I was planning on using the Blackboard to give a quick and dirty introduction to model categories, but I didn't have time to write it up as slides because that involves diagrams, and diagrams are painfully slow to draw on slides. So I'm sorry about that, and I hope that people have some introduction to model categories. Right, so at least for this slide, you can think of path objects as being, let's say, path spaces in topological spaces. All right, and of types and objects being spaces, topological spaces. So identity types in a Quillen model category can be interpreted as path objects as long as types and contexts are interpreted as fibrations. So the introduction rule, in that case, this triangle, then truly becomes the factorization of this map in the model category as a trivial cofibration followed by fibration. And that's the definition of a path object over the object A. And the rules of elimination and computation for the identity type are given exactly by the lifting of this trivial cofibration against this fibration. Since this is a type that depends on the identity type of A, it is interpreted necessarily by fibration. And so this commutative square has a lift, and any such choice of lift gives us the elimination computation rules. What are path objects in a equivalent model category? Yes, that is all right. So think about nice topological spaces, and a path space for a nice topological space is the space of continuous maps from the interval to that space, right? In a nice enough model category, you might have some kind of object such that your model category, let's say, is Cartesian closed and or locally Cartesian closed, and exponentiating with that object gives you a path object. But in general, it's really an abstract definition. Maybe a homotopy theorist like Dan could provide a more.
Well, I mean, I think you can just emphasize that the diagram you drew there is the definition, right? It's a
Exactly,
factorization like it's drawn in the diagram you're pointing at now.
Yeah. So what I mean when I say that it's interpreted as the factorization of the diagonal as trivial cofibration followed by fibration is exactly saying that it is interpreted as the definition of the path object in the model category. So every model category comes with these factorizations of all its maps. And if you factorize the diagonal of any object, that gives you a path object as a trivial cofibration and fibration. Right. So here's an example. Let's try to get our hands dirty between syntax and semantics. So syntactically, you know that the type, the now probably very familiar type of I think it's called is contractible for a given type, big A. This type is the type of proofs that say that A is contractible. It's a mere proposition of contractibility of A, right? It says that a proof of contractibility of A is that A is inhabited and that every element is inhabited by some little a, and that every element is equal to A via the pi type. But of course, if you write this out as functions, this just says that this is a homotopy between the constant function on A and the identity function on big A, on the type A, right? And this thing is just saying that this is a deformation retract of the type A onto the terminal object, right? Because element of A is a map from the terminal object to A. Semantically, let's take a path object for A. Then what is this type interpreted as? Well, let's suppose we're in a locally Cartesian closed category, and so we can use sigmas and pi's, our adjoints, to pull back. And so the path object, we can first take the right adjoint to pull back along the map. That's one of the projections. I think I wrote the second projection. Maybe I made a mistake here. But whatever, one of the projections. And then followed by the composition map, which just forgets, in this case, that we're living over A. And so a section of this thing, well, what is it? I can post-compose this with the, so this thing is, as an object, exactly the same as this guy, and it lives over A. And so I can post-compose this with A that gives me a section of A, right? But it doesn't just give me a section of A, it gives me a map into this thing that lives over A. But by adjointness, this is the same thing as a triangle like so. And this is exactly a right homotopy between the constant map on A and the identity map on the object A. So if you think about topological spaces, this thing is a map from A into paths in A, and that the two endpoints of the path that's being drawn give you the two functions from A to A. One is just the constant function on A, and the other is the function that's the identity. The constant function on little a. Maybe I should have called it something else. And this is just a deformation retract of A onto 1. Does that make sense? So going from syntax to semantics via the identity types as path objects interpretation. All right, so now we accelerate a little bit. And it turns out that there is roughly the same time as Awodey Warren's work, Voevodsky constructed a particular example of a model category that models all of bare homotopy type theory, by which I mean sigmas, pi's, identity types, and a univalent universe. So with the univalence axiom. What does that involve? Well, there is a nice model category on the category of simplicial sets. They had a category of simplicial sets. It's a Grothendieck 1 topos in particular. It's a locally Cartesian closed category. It satisfies a lot more nice properties. It's locally presentable, etc., etc. It's a pre-sheaf category. And there is a model structure on it that's called the Kapulkin model structure. I won't go into details because I haven't told you what a model structure is. But Voevodsky's construction is essentially defining for a suitable large enough cardinal kappa, a kappa small map of simplicial sets. So morphism in the category of simplicial sets that is a universe in the sense of what we've been talking about of kappa small fibrations, of all kappa small fibrations in this model structure. So kappa small fibration is a fibration that as a morphism is kappa small, and being kappa small is this thing. Moreover, this universe is closed under sigmas, pi's, and identities type constructions. I didn't tell you what being closed under identity type constructions is, but I didn't really tell you what being closed under sigmas and pi's are. So a universe can once again be closed under identity type constructions. So this is essentially in the model category. This would be that constructing path objects gives you kappa small fibrations from kappa small fibrations. Moreover, the codomain of this map is a fibron object, and this map itself is a kappa small fibration. And this universe satisfies the univalence axiom. And I'll get to what satisfying the univalence axiom means. All right, so I won't talk about the construction of this fibration. Constructing this is somewhat technical. It uses some stuff about well orderings that basically is due to the fact that we're working in pre-sheaves on sets, pre-sheaves of sets. But it is a fibration, and it does classify kappa small fibrations with some well orderings involved. But I'm more interested in talking about why the codomain is fibrant and what we mean by univalence. So firstly, why this thing classifies kappa small fibrations, moreover, why the universe is a fibron object, and why it satisfies the univalence axiom. Right, so classifying small or kappa small fibrations. In order to do so, it suffices, so the original proof goes as follows. We show that in any diagram that's the solid diagram over here, so leaving out the dashed arrows, in which the vertical arrows are fibrations, so kappa small fibrations. The arrow from A to B is a monomorphism, that is a cofibration of simplicial sets. And the squares are pullbacks. So the solid square at the back here and the solid square into the universe are both pullbacks, then there exists the dashed arrows making everything commute, and that this is also a pullback. And why does this say that every small fibration is a pullback of this thing? Well, you could just take U to be the empty simplicial set, in which case you just have a fibration and no other data. You could take A to be the empty simplicial set, and in which case X is also the empty simplicial set. And therefore, you just have a fibration over here. And what this says is that there exists a classifying pullback square. But this property turns out to be more useful because, in particular, it allows us to show that being fibrant for the universe reduces to something called the fibration extension property. And the fibration extension property says that fibrations extend along trivial cofibrations. So given a vertical map, that's a fibration, and a horizontal map, that's a trivial cofibration, we can find a, the question is not just a monomorphism. So I glossed over this part, but in the model category of simplicial sets, monomorphisms are exactly the cofibrations. So map is a cofibration if and only if it's a monomorphism. And that's going to be important. That's actually very important to models of type theory. So, all right. So showing that the universe is fibrant turns out to reduce to this fibration extension property, and showing that the universe is univalent boils down to showing an equivalence extension property. So what that means is that given vertical maps, by vertical maps, I mean X to A, Y to A, and Y prime to B, that are fibrations, and given a weak equivalence from X to Y, as well as a square that's a pullback that lives over a cofibration I, there exists a square at the back that's a pullback, and so all three squares are a pullback. And moreover, V is a weak equivalence. Now, if I had a blackboard, I would be able to describe why showing univalence boils down to this, but I don't have a blackboard, so.
There's a question. Someone has their hand raised, so I will let them.
All right, yeah.
So Harold, you have your hand raised. No, hand is not raised anymore. Okay.
Right. So, all right. Okay, so if you want more details about this, I can maybe try to kind of hack together an explanation using my notebook, my physical notebook, and the computer camera. Let's see how that works at the end of the talk. All right, so models in higher topoi. Well, the model in simplicial sets, I really haven't described it to you, but that's more for lack of a blackboard and my own, I guess, forgetfulness. I should have checked to see the, anyway. The model category of simplicial sets presents an infinity topos. So what that means is that up to homotopy, when you consider the objects of the category, fibrant cofibrant objects of the category, and morphisms up to homotopy, so composition of morphisms up to coherent homotopy, this forms an infinity category. And this infinity category, infinity one category, is an infinity one topos. And moreover, it's the infinity one topos of infinity groupoids. So it's like the role that sets, the category of sets plays for one toposes is the role that the category of infinity groupoids or spaces plays for infinity toposes. And the model of homotopy type theory in simplicial sets does in fact interpret types as arbitrary infinity groupoids, because there's some size condition involved, but it's possible to extend that to any cardinal. So it does allow you to interpret types of HoTT as arbitrary infinity groupoids. So in fact, when doing homotopy type theory, there is an interpretation of everything that we're doing in spaces, in arbitrary infinity groupoids. So anything that you prove in HoTT is true for spaces. However, there are more infinity toposes than spaces. And in fact, infinity toposes that behave quite differently to spaces. And indeed, it's possible to extend this construction for simplicial sets to an interpretation of HoTT in any infinity topos. So where types or contexts are interpreted as arbitrary objects of any infinity topos. And so the special properties of the infinity topos of infinity groupoids cannot be captured by HoTT. So for example, the infinity topos of infinity groupoids is hypercomplete for people who know what that is, but you can't say that HoTT that is hypercomplete because it can be interpreted in infinity toposes that are not hypercomplete. Right. So in order to do this, the basic tool that's actually a quite recent introduction is that of a type theoretic model topos. So a type theoretic model topos is, yes, I would talk about elementary infinity topi, but there is a little bit of hesitation on what exactly elementary infinity topi are. So maybe we leave that to another time. In any case, already being able to interpret HoTT in arbitrary infinity topi, Grothendieck infinity topi, is already very powerful. For example, modalities and things like that are make a lot of sense in infinity topi that are not spaces. Right. So type theoretic model topos is a category that's a one topos that has a model structure that's right proper, combinatorial, simplicial, and whose cofibrations are exactly the monomorphisms. This last condition is called being a Szynski model structure. It is simplicially locally Cartesian closed. So the adjoints in the local Cartesian closure are simplicial adjunctions, the adjunctions of simplically enriched categories. And it has a suitable notion of fibered structure, which is a really terrible name, although I suppose Mike doesn't agree, which is essentially what plays the role of a universe, except that the universe in simplicial sets is nice enough to allow us to get away with describing a good old universe, whereas in other situations of type theoretic model topi, what we end up with is a notion of fibered structure that is more difficult to define, that has more structure than what the universe of simplicial sets has, but that always allows us to obtain at the end a map in the category, in the one category E, that is a universe in that one category E that classifies all fibrations. But we obtain that universe from a notion of fibered structure. Right. So the key fact is that every type theoretic model topos models essentially HoTT. So most of your usual constructions in HoTT, so of course univalence, everything up to univalence, but also different kinds of inductive types and higher inductive types can be interpreted in any type theoretic model topos. Moreover, a type theoretic model topos always models an infinity one topos. All right, so how does one get to arbitrary infinity topi, Grothendieck infinity topi from type theory? Well, it so happens that there is a very good model category that can be associated to any Grothendieck infinity one topos. Its underlying one category is a category of simplicial presheaves. So it's here I've taken a small category, a small one category A, but in general, what we would consider a small simplicially enriched category A, and the category of simplically enriched presheaves on A. But any such category of presheaves has a so-called injective model structure that is its weak equivalences and its cofibrations are the pointwise weak equivalences and cofibrations of simplicial presheaves, and the fibrations are defined as those that have the right lifting property against the trivial cofibrations. And it so happens that every Grothendieck infinity topos can be presented by what's called a left exact, left Bousby localization of one of these injective model categories of simplicial presheaves. So to begin with, it would be nice if the injective model categories of simplicial presheaves were type theoretic model topoi. However, this is a lot trickier than in the case of simplicial sets. And why is that? That's because the fibrations of this injective model structure are difficult to characterize. So for people who know, there are other model structures that present the same infinity topos, the presheaf infinity topos, like the projective model structure, but those are obviously not type theoretic because they don't have their cofibrations are not all the monomorphisms, right? So projective cofibrations are not all monomorphisms. Not all monomorphisms are projective cofibrations. Right, so constructing a universal univalent fibration is non-trivial compared to the same construction for simplicial sets. And the main tool that Mike's paper solves is a new characterization, I think, of injective fibrations or fibrations in an injective model structure, which is essentially that injective fibrations are difficult to characterize for the following reason. If you take a square of simplicial, a commutative square of simplicial presheaves, where on the left we have a pointwise cofibration, and on the right we have a pointwise fibration, then pointwise there exist lifts. Sorry, I should have said trivial cofibration. That's a mistake over here. So on the left, we have a cofibration that's a weak equivalence, so pointwise a cofibration and pointwise a weak equivalence. And on the right, we have a pointwise fibration. Then pointwise, we have a lift of the square. That is, we have lifts CA to XA for all little a in A. But these, however, don't fit into a natural transformation. They do fit into a homotopy coherent natural transformation. What that means is that the naturality squares commute up to a specified homotopy in simplicial sets, and that composing homotopies for composed squares is the composite homotopy, once again, up to a higher homotopy, and so on, and so on, and so on. And that's what a homotopy coherent natural transformation is. But there exists a construction that reifies homotopy coherent natural transformations into a classifying simplicial presheaf. So there, for any object X, there is, for any simplicial presheaf X, there is a simplicial presheaf C of X that classifies homotopy coherent natural transformations into X. What that means is that a strict natural transformation into C of X is a homotopy natural transformation into X. And this is called the two-sided Kobar construction. And this comes with a map from X to C of X. And it just so happens that X is injectively fibrant just when it is pointwise fibrant. So I missed that out. It has to be pointwise fibrant. And when this map is equipped with a retraction, the retraction simply being that any homotopy coherent natural transformation into X can be strictified. That's what the retraction does. But retractions of a map are structure. And so this turns out to be a suitable notion of fibered structure instead of simply being a class of maps that's stable under pullback. So once we choose retractions that are stable under pullback, which is essentially what's contained in the data that a notion of fibered structure encodes, we can do essentially these same constructions over here, where previously we were only bothered of about getting this to work, about mere existence of fibrations and of squares. Here we need to have a little more structure and things that are natural in the rest of the diagram. So the structure has to commute with the rest of the diagram. All of these things have to be morphisms of that structure rather than simply being a fibration. So instead of having this just be an injective fibration, we would have that this thing is an injective fibration with an equipped structure that makes it, which has the corresponding retraction of the map into the two-sided cobar construction, the relative cobar construction. That's what you get when instead of an object you take a map. Anyway, so this is what is essentially captured by the notion of fiber structure that makes simplicial presheaves on a small category with the injective model structure a type theoretic model topos. And then it's possible to essentially show that this passes through left exact left Gauss field localization. Of course, that would be a talk to give on a blackboard. And I'm really sorry for not having a blackboard, so I think I will stop here since I've run out of slides.
Great. Well, thank you very much, Chaitanya. I can't get everyone to unmute and applaud in this format, so you have to just trust or look in the chat and see people thanking you. But I will open the floor to questions. They can be in the chat, or you can just raise your hand. I can get the ball rolling with one question. Do you want to say anything about the issues having to do with coherence with modeling HoTT?
Right. So every time I mention something like this, I was brushing under the rug a problem that it has to do with the strictness of syntax. What that means is that that's what you mean by coherence, right? Okay. So the strictness of syntax makes all of these constructions, here, all of this structure on C strictly stable. What that means is it's stable under substitution, but that also all of these choices of structure are strictly associative, and that the choices for identity are essentially like the identity, literally the identity, pullback squares, for example, in all of this structure on the syntactic category. And that when we model syntax in another category, the only way to have this be an actual functor of one categories is to equip our model with a similarly functorial choice of structure. And one way to get away from having to do too much of this is to start with a universe and to define everything relative to a universe, which is what I meant when I talked about defining a model of type theory in an LCCC equipped with a universe. So once you have a model in an LCCC equipped with the universe, a lot of your constructions are automatically stable, strictly functorially by base change, by substitution. There are other size issues to consider, which is that in one category, map can only hit maps of a certain size. So a universe can only classify maps that are small for some cardinal. But there are other ways to, for me, that's not really an objection, because in most situations you can increase the size of your cardinal to get a similar universe that classifies things for any given cardinal. All right, so hypercomplete. Okay. So Right.
Could you read the question out loud for the video?
Yes, so the question is, could you spend a second explaining what hypercomplete means? All right, so you've seen what to be connected is, n-connected. Yes, I think. N-connected and n-truncated. Yeah. So is it the case that a map that is n-connected for all n is invertible? So it has contractible fibers. This is not provable in HoTT, precisely because this is what it means for an object of an infinity topos to be a map of an infinity topos to be hypercomplete, I guess. It's the hypercompletion of an infinity topos is to invert all of its infinity connected maps. So maps that are connected for all n connected for all n.
Maybe one thing to add is that for some people who've had a first course in algebraic topology, or maybe a second course, Whitehead's theorem is the question here. So,
yeah,
you know, we usually say it as if a map induces an isomorphism in homotopy groups, then it is an equivalence.
Exactly.
And that holds for spaces, but it doesn't hold in every infinity topos. And
yes,
you can't prove it in HoTT.
Yeah. And one way of showing that you can't prove it in HoTT is to say that you have a model of HoTT in any Grothendieck infinity topos.
Yeah, and that brings up another reason that you could have put on your first slide for a motivation for semantics.
Mm-hmm.
It's to show things that you can't prove.
Yeah.
You know, if you're wondering whether some statement's provable in HoTT, you often go looking for a model where you can show it's not true.
Yeah.
And then you know you should stop trying to prove it. Okay, I see another question in the chat.
Is there a bridge between type theory and test categories? Right. So, well, in the traditional notion of test categories for, I guess, the fundamental localizer, I mean, any localizer is like a localization of the fundamental localizer, but for the fundamental localizer, the traditional theory of test categories shows you how to obtain a model structure that models spaces on ordinary presheaves on a test category. Right? This thing need not be a type theoretic model structure, and yeah, I guess that yeah, maybe you should ask someone like Ulrich on the Discord. Might have a better answer than I do. So yes, so certain ready model structures, well, there are certain ready categories called elegant ready categories where the ready model structure coincides with the injective model structure. That is, ready cofibrations are all the injective cofibrations. Every injective cofibration is a ready cofibration. And so in those cases, type theoretic model toposes arise from ready model structures. But in the general case, not all monomorphisms are ready cofibrations. So that would preclude. Yeah, sure, I can make the slides available.
Okay, any last questions?
Yeah, so that's a good question. So as far as I know, there are some models that do something slightly different, which is to use algebraic weak factorization systems. And so, and there are other model structures that are constructive model structures. on simplicial sets that essentially obtain the same infinity category. So I do know that in some cases, cofibrations are not all the monomorphisms, but you can still have at least a model structure. I don't know about interpreting type theory and those model structures. Maybe Emily would be a good person to ask, and Christian Zattler.
Okay, well, let's thank Chaitanya again. And I'm also going to share something here. Okay, so this is a good point where we should thank everyone who helped put this summer school together. I hope you all enjoyed it, and it was a big team effort. You can see all the different people here who either spoke or did TA work behind the scenes or were organizers. So maybe when this talk's over, you can go on the Discord and express your thanks there. The regular hottest talks are going to start in October. So I hope a lot of you who've joined the summer school will also join us to attend those talks. So that's it for now. And I will stop the recording.